the last talk today by Vivien Parmentier on cloudy atmospheres.
Hi everybody. So I'm Vivien Parmentier. I just defended my PhD 2 weeks ago from the Observatoire de la Côte d'Azur, and I'll be moving to UCSC next year. So following the very nice review from Kevin about clouds in exoplanets and what space photometry can teach us, I'll try to continue a little bit here by presenting you some results from our 3D modeling of clouds in irradiated exoplanets. And I try to have a second part of this talk to discuss how space photometry data can tell us actually about the atmospheric composition via measuring the radius of the planet. So first, let's discuss about clouds. As you've seen in the talks of Kevin, clouds seems everywhere in hot Jupiters for the moment. Yes, many hot Jupiters with cloud patterns. And let's discuss a little bit a very simplistic view of cloud formation. So if you can imagine here a pressure temperature profile of a typical hot Jupiter. So here you have the top of the atmosphere, bottom of the atmosphere. And this is the condensation curve of minor species in the atmosphere. So here the solid phase is stable, here the gas phase is stable. So what should happen here? The particles that are here, gaseous particles that are here, will diffuse through the planet, cross the condensation curve, make particles that will rain out from a cloud deck here, and gaseous species can be the vertical extent of the clouds and the amount of gaseous species that remain in the atmosphere will be determined by the vertical mixing that can happen in the planet. So why do we care about clouds? First, why do I care about clouds? Because clouds are tracers of the atmospheric circulations. Because you need mixing by the circulation from clouds. Observing clouds can tell you about the circulation. Second, they definitely affect the chemical abundance of the species that does condense. Because if they're condensed, they're less abundant. So when you observe, when you derive chemical abundance in a planet, you have to take into account whether it is partly condensed to determine the bulk abundance of your planet. And finally, as shown by Kevin, the clouds can, a cloud deck in the planet can hide species below the cloud deck, and that will be a strong bias in the retrieved bulk chemical abundance. So here in this talk I will focus in 3 specific planets for which hints of clouds have been detected. So the first one here, Ig209, which has an equilibrium temperature for 0 albedo of 1500 Kelvin. There's some clouds that seems to affect the signature of water in transmission spectrum, and that impede us to determine the exact amount of water in this planet. Then I'll discuss a little bit about Kepler 7b. This planet have an equilibrium temperature for 0 albedo that is quite similar to Ig209, but due to its large albedo, the final equilibrium temperature of the planet is slightly smaller. And finally, I'll discuss a little bit about HD 18973b, which are new simulations that we carried out, where we have the most evidence for clouds. So, how do we study? How do we want to study those hot Jupiters? So, one of the main points of hot Jupiters is that they are 3D objects, and to model 3D objects, you need 3D models. And so we use the MIT GCM. So we solved the equation of hydrodynamics on a cubic sphere grid on a large domain of pressure with a radiated transfer that is quite complex, taking into account many chemical species. And so let's begin with Ig209 for 5E. So here are the results of the temperature map, only the temperature of the planet, as predicted by the GCM. So you see typical features of a hot Jupiter, which is that the dayside, the planet is tidally locked, so the dayside is hot here, and the night side is cold. And you can have very large temperature gradients between the two. So this is latitude, longitude, and pressure, longitude. You see also a second point that was mentioned by Kevin, is that the hottest spot is shifted east of the substellar point. Okay. So the first and most simple cloud model that you can try to put inside your model here is to say, oh, the day side is hot, the night side is cold. So what do I expect? I expect no clouds in the day side. It's too hot for clouds. It's more than, it can be up to 2000 degrees, whereas in the night side, it should be cloudy. So we actually use the MIT GCM and modify it by implementing passive tracers in the GCM. So in the cloudless areas, the passive tracers, they just follow the fluid. In the cloudy area, where my chemical species is supposed to rain, they additionally have a settling velocity that is done to mimic the rain. And the settling time scale is given by the size of the condensate. So this concerns many planets, because there's some studies showing that the day-night contrast might increase with the equilibrium temperature. So even for hot planets, you still expect a relatively cool night side. And it concerns many species, like TIO, iron, NGS, IO4, etc. So, and why do we do such, if I come back here, why do we use such a simple here? 3D models are very complex, so it's good to first look at a simple case. We are not looking at exactly where the transition here, where does the temperature map crosses the condensation curve. And we'll see that this has effects after. So this is some results of the cloud abundance from the GCM for the planet HD 209458b. So this is the limb of the planet. So you have to imagine the planet that is transiting its host star. And for particles of 0.1 micrometer, so here the North Pole, the South Pole, the East, the West, the planet transits this way. And this is pressure in a log of the pressure. So you can see that for 0.1 micron particles, they're expected to be everywhere. 1 micron particles, they're slightly depleted, whereas more than 10 micron particles are completely depleted from the atmosphere of the planet. So what do models tell us? That we expect maximum particle size of around 1 micrometer, which is for the moment consistent with the few observations that exist. And here, what can we try to learn? Why is that important? Is because the top cloud pressure is fundamental to quantify the molecular abundances. Basically, the point is that if you're looking for water in an exoplanet, and you have this planet with those clouds, you're actually only probing by transit spectrophotometry this small clear sky, the part of the planet that is completely clear. And if you assume that the water you see there is actually dispatched everywhere in the planet, you completely changes your estimation of the bulk abundance of the water in this planet. But what space photometry can tell us in these planets, because as you've just seen before, we are considering that the clouds are condensing in the night side of the planet. But the actual place where the condensation line will cross the temperature profile might be slightly displaced a little bit before or a little bit after the terminator. If it's a little bit before the terminator, it should be cloudy everywhere. If it's slightly after, as we've seen that the hotspot is shifted to the east, actually I might have no clouds on the west, but clouds on the east side. And so, is the gas really condensed at the limb of the planet? So phase mapping of the dayside albedo of the planet can help to disentangle this problem. So we now go toward Kepler 7b, where this famous mapping has actually been done. And so you can see here, again, a temperature map of at the equatorial plane of Kepler 7b. So again, pressure and longitude is from a paper in preparation by Nicole Lewis. And you can see overplotted several condensation curves. And so, slightly differently from the case of HG209, here we do have a significant portion of the dayside that is expected to be have temperature lower than the condensation temperature. And actually, if we look at the light curve of Kepler 7b that Kevin presented, here it's shifted to the east, the maximum of the light curve is shifted after the secondary eclipse. And so I derived a small analytical model based on a paper from Madhusudan, 2012, I think, which consider what would be the phase curve of a planet that is partially clouded, that have an albedo omega-1 on the west and omega-2 on the east. And the good point of such a simple model is that it can actually give you a retrieval of the different values of the albedo. And the phi c is the longitude of the cloudy to cloudless separation. And so we see that we get omega-1 that's close to 1, which is similar to cloudy atmosphere, and omega-2 that is around 0.1, which is close to, a little bit high, but close to what you expect from a clear K atmosphere. And a phi c that is minus 40 degrees compared to the substellar point. So if we come back to the temperature map, here, this is compatible, the light curve is compatible with here, so clouds down to minus 14 degrees. So this is compatible clearly with the temperature output from the GCM for this planet. So let's look at a third case, which is slightly cooler, HD 18973b, which is the TX01200K. So same thing, if I begin with to look at the temperature map of HD 18973b. So here I have the equatorial temperature map, so the pressure, longitude again, and I'm not sure if you focus about the numbers before, but I'm slightly cooler than in the case of Kepler 7b, and most of the condensation curve that I show were following the 1400 Kelvin isotherm. So here in HD 18973b, what do I expect for the condensation? It's this, and the schematic view will be this one. Above a given pressure, I'll be in a condensed phase, and below I'll be in a gaseous phase. So we run here the models for HD 18973b. And so you can see here the output, so that's the dayside quantity of tracers in the planet. So for 0.01 micrometer, for particles of 0.01 micrometer, you see that you have particles almost everywhere. They're very easy to lift. For 0.1 micrometer, you begin to see some structure in the planet. And for 1 micrometer, you definitely have a bonding that begins to appear in this planet. And we are looking actually if this bonding, can we see such a large variation in clouds? Because if you imagine here, you should have an albedo of 1 on the poles, but almost a 0 albedo at the equator. And so first estimation that we provide with, that we've been doing with Julien de Witt says that, so there are, we haven't done the exact calculation, but we extrapolate for some other calculation that we've done slightly before to have a first answer to this conference. And it seems that with tens of eclipses for favorable target with plateau, using the secondary eclipse mapping, we could, in theory, be able to see this difference. Practically, there's obviously many problems that we'll have to overcome. But since with plateau we'll have these tens of eclipses for some bright targets, we should definitely try to see if something is possible. So finally here, we see, as a small conclusion of this first part, we see that we study HD 20945AB, where clouds might be present at the limb, which is very important for transit observations. For Kepler 7b, we have partly cloudy dayside, and so longitudinal variations that can be probed by space photometry. And for HD 18973b, we expect also from the models, we expect a partly cloudy dayside. But due to latitudinal variations that might be probed with future instruments. Okay, so now I'll switch to very rapidly to another topic. So I'll talk a little bit about bulk atmospheric composition and how can we relate that to planet evolution and how photometric data will help us to by an indirect way to constrain the atmospheric composition. So, as most of you might know here, a gas giant planet does not keep the same radius during all its lifetime, and it slightly contracts by gravitational forces over time. As it contracts, it heats up, and the pressure counterbalance the gravity forces. And the planets continue by cooling down. It can continue to shrink over time, and so the radius of the planet decreases as the temperature of the planet decreases over time. But to get rid of all its internal energy, the energy needs to cross the atmosphere, which surrounds the planet by definition. And so the atmosphere must really be seen as a valve that can determine how much energy can escape from the planet. And so the composition of the atmosphere might be of great importance to determine this cooling rate. So here I take an example of a titanium oxide that is expected in the dayside of hot Jupiters, given their high temperatures, but that have not definitely not been seen for the moment. So this is a great problem that the community is trying to figure out now. Is there TIO on these planets, and if there is not, why? But here, let's consider the two cases. Imagine a planet with titanium oxide that would give you the temperature profile, the red one, and a planet without titanium oxide would give you the blue one. Why? It's very simple. It's because titanium oxide is a very good absorber in the visible, and so should absorb the stellar light in the upper atmosphere, and so cool down the deep atmosphere. So what we've done is that we created a grid of numerical models of pressure, temperature profiles for irradiated exoplanets using a numerical code of Fortney, Marley, McKay that consider solar composition atmospheres. And we used together an analytical model that we derived, which is a non-gray analytical model for irradiated atmospheres. And we calibrated the coefficients of our model to match the best we can the grid of numerical model. And so we end up with a model that works within 10% over the whole large range of irradiation and gravity. So we have a case we calibrated with a case with titanium oxide and a case without titanium oxide. So you can see the different profiles that are flipping between the two compositions. So with this analytical model that is calibrated on a grid of numerical models, so we do have this analytical model that, by the way, can be downloaded here at this address. So we use this model as a boundary condition of the CEPAM, which is a code for modeling the internal structure and evolution of exoplanets. That Mathieu Havel will tell you more tomorrow about this. And so we can calculate the radius evolution of a planet with titanium oxide and without titanium oxide, for example. And what do we see is that the presence of titanium oxide in the atmosphere actually increases the cooling rate of the planet. So all things being equal, and this is very important, planets with TIO in their atmosphere should be smaller than planets without TIO in their atmospheres. And I'm saying that about TIO, but this is definitely applicable to any compound that will change the deep temperature profile. So sodium, for example, might be an interesting example to look at, and clouds would definitely change the deep temperature profile of a planet. So just to finish, do we see that in the data? So this is the radius of the planet as a function of the equilibrium temperature. And if this theory were right, we would expect for cold planets that are too cold to have gaseous TIO, hot planets are too hot enough to have gaseous TIO. So we would expect to have a small step here of this order of magnitude between the two populations. Clearly, for the moment, I won't bet anything that this is true or untrue. But this was just to mention that with space photometry and with measuring radius, we might actually be able to constrain composition of exoplanets atmosphere. So as a conclusion here, we saw that the atmospheric circulation should shape the clouds in planet atmosphere, and in particular in hot Jupiters. We are lucky because the patterns, circulation patterns, are global and thus may be observable by photometric missions. The second point is that atmospheric composition can affect the long-term evolution of the planet, and statistical studies are needed with a large sample of planets measured with a good precision. Thank you very much for your attention.
Yeah, thank you. Okay, first question.
Well, you show the temperature profile in the atmosphere of the planet, so how the temperature changed. And in the higher layers, there's the heating by the extreme ultraviolet radiation and the X-ray radiation. How did you include it? Because I didn't see the reheating of the upper layers in the atmosphere.
Yeah, you mean here?
Yeah.
We definitely, the opacity database that we're using stops around 300, 400 nanometers. So we are definitely not considering UV heating in those models. But I mean, do they affect it down to the 10 to the minus 4 bar?
Oh yes, oh yes. Think of the Earth atmosphere.
Okay, thank you. Kevin, what's the next?
Okay, to answer your question, photochemistry is more important on planets with moderate temperatures, so you expect it on HD 189 and not on HD 209. And this has been demonstrated in the papers of Julie Moses in 2011, for example. I have one comment about your slide about effective temperature, actually two comments. The first comment is that this story about TIO, no TIO, PM, PL planets has been made by Fortney et al. In 2008, so it's not new. And the second is that the equilibrium temperature is a misleading quantity for thinking about temperatures in the atmosphere. So think of Earth and Venus, right? They have about the same equilibrium temperature, but the temperatures are not the same. So that's just a word of caution.
Any other questions?
So I have a question about your modeling of Kepler, what is Kepler 7b? Just you're putting a longitudinal dependence of the cloud distribution to explain the phase curve shift related to the secondary eclipse. So I just want to make sure there's no fundamental reason why it should be shifted west, right? Is there a fundamental physics reason? I mean, could have been other way, right?
Oh, for the
shift.
Well, the reason you can think that this might be a good explanation, and it's actually already in the paper of Demory et al. That presented the phase curve, is that hot Jupiter's models, that's what we were Kevin and Isabel were discussing just before, is that we believe that the hottest spot of the planet is shifted east of the substellar point, which is due to super rotating winds that are in this planet. And so if you just take your pen and draw where do you believe clouds should be in this planet, just based on the condensation curve, you would expect more clouds on the west side of the dayside.
Good, okay.
Any other questions?
Here, Susanne.
So, given that these simplified models of using condensation curve to work out what sort of clouds should form where in planetary atmospheres systematically fail for every planet in the solar system in terms of the clouds we can observe, how come they work at all for exoplanets?
Let's say that, well, there's at least, well, I don't believe that they work really for exoplanets. That's the first point. The second point is that for hot Jupiters, we are kind of lucky compared to solar system planets in the fact that there's many arguments to believe that the atmospheric circulation is dominated by very large scales, which are planetary scales added, and that we can actually resolve with the GCMs. And that do gives some patterns in the cloud patterns. And I mean, we are just really at the beginning on the only observation of spatial variation of clouds is Kepler 7b on the phase curve that you've seen. And yeah, so I'm not, it might, for Kepler 7, in one example, if it might be a pure coincidence, so there might be other explanation, but these arguments of large-scale structures make it that we can believe that maybe this is actually working and we'll understand it better in the future.
Yeah, my question wasn't really about the structure that the GCM predict, which does seem to be quite robust, but more about, you know, if you look at a particular locality in the atmosphere, you work out what the temperature should be, and you work out what sort of things should condense at that temperature, and then you predict what sort of cloud you might expect to see, therefore the composition of the clouds. Very often in the solar system it doesn't work because the cloud particles are coated in something else or something like that. But I was just wondering if maybe there's something about the fact that these planets are so hot, and therefore their clouds are made of completely different stuff, that might make it easier to predict, or not. I don't know. It wasn't meant to be an attack of GCM modeling of exoplanets.
I mean, for the moment, we have no idea of the composition of those clouds, to be clear. We have no observational evidences. What makes it kind of easier in those planets, not sure if easier is a good term, but different, is that we believe that there is very strong temperature gradient. So if you take a piece of dayside atmosphere, you bring it on the night side, you have no choice that like TIO should condense, because you have a 1000 Kelvin drop in the atmosphere, and the saturation goes as exponential of the temperature. So this simple idea is that you are condensing only in the night side does have a physical justification for those hot Jupiters.
Right. A question about whether radiator transfer is included in the GCMs and how.
Yes, so the radiative transfer we use is in this GCM is one of the most sophisticated used in hot Jupiter GCM for the moment. We use the correlated K coefficient methods to sample the opacities, and we use like 5 angle of integration. The main caveat here is that we actually don't consider the effect of clouds in the radiative transfer for the moment. And so let's say in AG209, that's one of the reasons why we're considering first clouds that condense in the night side, because if they condense in the night side, we are not that false by neglecting the radiative transfer of clouds, because at least in the visible, they don't matter because they're not in the night side, in the dayside. For HD189, you saw this banded structure. So we are performing simulations with a very simplified version of the radiative transfer for clouds in the dayside, and the structure seems to persist. So now we want to understand more deeply what creates this structure.
Okay, then thank you. We will close this afternoon session. Thank you, the speaker. And Rafa wants to say something.
It's okay.